Hello, welcome to the video for the Prototype 1 development from the 28th of May. Just to start off with some overview pictures, so some changes in the sliding mechanism, just continuing to refine it. Yeah, you'll notice certain parts are hidden from the frame plates, which is intentional. We've adjusted the mechanism housing slightly, and have of course removed the tactical rail from the front. And so here's how it's looking at the moment. It's just worth noting this is now all with 12 gauge barrels moving forward. So sliding mechanism concepting. So this is the solution overview. So this is the most up-to-date version. Looking pretty similar to what you've seen, apart from I've added this little central part here, which I'll go into more detail. That's for the reset actuator that lies in the center. So that's both how it's fixed and how it's sprung. I've also slightly modified the latch. I've modified the striker head, as you can see, with the little notch in the side. And I've also removed the frame plate from the heavy spring side, just to give the heavy spring a bit more room, and also because it's unnecessary, so we can save some weight there. This image, so on the left we're seeing the sliding mechanism in full, and that's just zooming in on the frame plate on the heavy spring side, which has been removed. A little bit confusingly, this image on the right, so the light frame plate is just hidden here, just so you can see more detail. So we've got this split latch design, which is sprung from the frame plate. Yeah, just exposes some of the inner workings. So in order to finish off the design for the sliding mechanism, I did a operations check in PowerPoint, which was actually really useful. There's a lot of different parts to consider. The striker, the ratchet latch, the latch tension spring, the hammer, the latch itself, all of these things move together, and it's quite difficult to work out how it all works without going through the motions. So the regular operation, so the top barrel to the right, then to the bottom, then to the left, so we're moving clockwise as you're looking down the barrels of the gun. Here we've got the nominal position, so the hammers are forward, nothing's cocked just yet. As we pull the trigger, the hammer is partially rotated. This forces this latch. Actually, I'll just turn on the laser pointer so hopefully you can see my mouse. This forces this latch into the striker, and the striker begins to rotate. This striker ratchet assembly is all fixed together rotationally, so this whole thing rotates, and it pushes this latch, pushes the ratchet latch aside as it rotates. Moving the hammer all the way back, we're now in the fully cocked position, so the ratchet is actually been over rotated. So by the ratchet I mean the entire striker and ratchet mechanism. So you can see just here would be the sort of 90 degrees rotation, so that started at the top and it's come around, and it's actually being over rotated slightly. This is just so we don't have to worry about any really precise tolerances. You know, we're not catching this latch by half a degree of rotation. It doesn't have to be perfect. It's designed to over rotate and then catch again. In this current position, you can see the ratchet latch is actually being held an outward position. That is by intent. So at this position, the striker is actually being held in place still by the main striker latch, as you can see here. As the hammer's released, the striker latch is still holding on to the striker as it's coming forward, but as it comes forward, the ratchet latch then moves off this little ramp in the central frame plate and engages with the ratchet, so that as the hammer gains momentum and leaves the striker latch behind, so just to remind you, that's this the longer latch on the side, this one, as it leaves that behind, the striker is then sprung against the ratchet latch, and is then fixed in place. So that's how we're going from the top barrel position to the right barrel position, but it's exactly the same process from the right to the bottom and then the bottom to the left. The left of the top barrel is now a new case. So we've got an internal spring which is putting tension on this striker head as it's rotating, and it can't keep going and going. It needs to rotate back round to the nominal position. So we have been going clockwise, and on this next movement we'll go anti-clockwise. So once that left barrel has been fired rather, the striker assembly is now under rotational tension and wants to return. If we release it at any point, it will just return to the top barrel position, and there's a hard stop designed into the striker ratchet so that it will always be fixed at the top barrel position if it's not being held in place by anything. So that's where it always wants to be. As the gun is cocked, you can just about make out a notch in the striker head just here. So as the gun is cocked in this particular striker position, the striker latch is actually completely bypassed. This means that the striker assembly does not rotate. As this comes back, we'll just go to the next slide. So as this comes back into the fully cocked position, you can see that the ratchet latch is then moved out of the way. Now, because we've bypassed the striker latch, there is nothing to hold the striker and the ratchet assembly in place, and therefore it snaps back to the top barrel position. Now, if we just had a completely solid striker latch, that would actually inhibit the movement of the striker coming forward. So we need a little bit of give, and that is quite simply achieved by just effectively putting a hinge in the middle of the latch. So this is a hinge. So actually, I'll just draw on this. So this is sort of the axis of the latch, and this hinge allows this front portion to angle down like this. So we're allowed to. It allows this kind of angle, and that bend is actually resisted by this spring just here. So the blue spring pulls the ratchet straight, and that red line is the most that it can deflect by, and it's because it's always in tension, it always wants to be straight. Now, as soon as a hammer comes back in typical operation and starts to move the striker latch back, it will keep straight. It's locked in position. It's just in this one particular case where the hammer's coming forward and it needs to bump the striker latch out of the way slightly. This hinge allows that front portion to move forward a bit, and then the spring, which we need anyway to return the striker latch to its nominal position after each firing, provides the tension on the striker latch to return it to this red line after it's been pushed out of the way. So at that point, the mechanism has been fully reset. So I've also refined the frame plate actuator, or the striker reset plate, actually, we'll call it from now on. So that's this cyan piece here. So the cyan piece, the job of this is that when the user breaks the barrels, this cyan piece is forced upwards, and that also pushes the ratchet latch to one side. What that means is that if the ratchet latch is holding any kind of tension, like holding the striker in a position other than the top position, it'll release that tension and allow the whole assembly to return to the top. So whenever this cyan piece is moved up, it resets the mechanism, and it's actuated by the act of breaking the barrels. So that's how you reset, is the idea. So every single time you break the barrels, once you close the gun again, it will always be on the top barrel. As you can see, the previous CAD on the left wasn't really a finished design. it was just showing the sort of design intent. So we wanted some sort of rod on the front and we wanted it to go up and down. I've now properly designed it, so it's a nice part. The way this fixes in place is just by a threaded rod. So you place so there's a threaded hole in the pink piece, which is the central frame plate, and you just place the striker reset plate on top, and then you place your compression spring on this threaded rod, and then screw the threaded rod into the assembly. So that then locks the striker reset plate in place, but it also provides the compression spring so that this wants to stay down, but then can move up when required. So that's a nice simple way of both fixing that in place and providing a spring force. So onto a slight modification to the mechanism housing. I've added a hole for the trigger unit. So the trigger unit is designed to insert from the bottom, and previously it was being fixed at either ends at points which hadn't actually been fully defined yet. I'm now using the trigger hinge itself as the main point to fix exactly where the trigger unit is going to sit in the mechanism housing. That's important because the tolerance that we can achieve between the hole for the sliding mechanism and the new hole for the trigger unit will quite comfortably be something along the lines of plus or minus 0.1 millimeters. So very accurate indeed, certainly much more accurate than the plastic 3D prints that we've done, and they work pretty well. So that makes life really easy. The idea behind this is that we essentially have a very small tolerance stack up. So we've got this hole and then the trigger straight away, which is mounted on the pin that goes through that hole. Similarly, we've got this hole, which serves the sliding mechanism, and that attaches very directly to the hammer. So that's just a way to make sure that our double single action mechanism will work nicely, and that these two completely separate sub-assemblies that we put in at separate points into the mechanism housing will actually gel together really well. So that's a nice and neat way of achieving that. So the video's already been seen, but yeah, just a slight refinement in the firing mechanism, doing 3D prints. One of the purposes of this was to get a print off to Theo as well. So on the right, in the red, is Theo's print. Works exactly the same as mine. It's exactly the same file. So I just sent that to him, and he could just print it right away. But this is an absolute success. Works really well. No real whittling required. So yeah, I mean, if we can correctly tolerance this in plastic and get this working nicely, then the metal should be absolutely fine. It's nice and smooth to use, nice and reliable, and the single action and the double action work quite well. And it also gives us nice insight into the relative strengths of the springs or elastic bands in this case. For example, the trigger, there's a latch that attaches to the trigger. You can't really see it just here, but if I just draw, there's an elastic band just around here, and you basically have your main trigger, which goes sort of, let's just do a very rough drawing, and then there's a latch which attaches to that trigger. That's your reset latch that works in your double action, and there's a spring which rotates this orange latch. The strength of this latch has to be balanced against this elastic band in this case, but this would be the trigger torsion spring. So just like how we have to match these spring strengths in the 3D print, we have to match it in real life as well. So just getting insights into what the sort of ratio would be, and the fact that we do need to do this and be quite careful about it is useful. And then finally, just to finish off, we've got the beginnings of engineering drawings. So the sliding mechanism is pretty much in a state where it's finished. will require a few changes here and there just to improve the manufacture, but I think most of those things will arise actually as we go through the drawings. So I'm keen to start the drawings at the moment, and this is for metallic prototyping, but we're doing those drawings with actual manufacturing in mind. So the important bits is what you see in this box. So the central frame plate we've got here is just an example, but you see in this box we've defined a machining standards, and I've gone for ISO 2768 medium. So what that means is it's a standard which basically defines how tight your tolerances should be depending on your dimensions. So for example, between 0 and 5 millimeters, you might want plus or minus 0.1 millimeter on your dimensions, and then between 5 and 10 millimeters, you might want plus or minus 0.2, and it kind of scales. So it's quite a useful metric to go on, and it means that we don't have to tolerance absolutely everything. We can just pick out specific points where we're like, okay, no, we need this to be particularly fine, or actually maybe this doesn't really matter, and then we can just go in and specify. So it's a good way of getting a reasonably accurate fit for all your components without much effort, and it's an industry standard, so we know that it works. At the moment, I've gone for medium. So how that works is, yeah, if you were designing something like an oil rig, you'd go for something really rough because you're not really too bothered. For a mechanism design, especially on the scale that we've got, it is quite fine. So we may wish to go for even 2768 fine rather than the M, which stands for medium. That kind of remains to be seen, and I'm going to review the standards in a bit more detail and kind of check against the tolerances that I've calculated that we need, and see what's appropriate. Again, the 3D print is pretty promising there. I mean, the 3D print is going to have relatively shocking tolerances when you compare that to metal. So the fact that the firing mechanism works pretty well, which is the area of highest tolerance, is pretty good. So I think medium's a sensible guess for now. In terms of the metal welding, yeah, 13920, it's just pretty standard. It's just to cover the few points that we do have welding in this design, and just make sure it's good. So good surface finish, correct welding methods, correct rod diameter. It just defines a few bits, and again, it's industry standard, so we just know it'll work, which is good. Have also defined a surface roughness. I need to look into this a bit further, but again, it's a case of just doing the best surface roughness that we need and no more. So I'll just look to compare information that I can find online with other firearms or just similar mechanisms. And then finally, there's just a specification to deburr, so any machining burrs that may arise, and also break sharp edges. Yeah, it's suitable for assembly. And that's pretty much it. So yeah, as mentioned, we'll start on the drawings pretty much from this point forwards. And just to reiterate, the point is to prototype the sliding mechanism and the trigger mechanism. So once we finish these drawings for the sliding mechanism, I'm keen to just order the assembly straight away and then come back and start working on the trigger mechanism drawings, and we can maybe do some parallel testing. And then once we've got those two mechanisms in metal, we'll then just do like a sort of 3D printed jig, maybe with some kind of brass inserts for the holes to make it slide nicely and hinge nicely. Make sure these two parts are interacting properly. And once we've got these two sub-assemblies working nicely, that's huge, and that's pretty much the primary risk, and then the rest of it is just really standard gun design. So yeah, that's all so far. Thanks very much for listening. Please feel free to contact me if you have any questions, and I'll catch you later.